So I guess I start. So yesterday, I spoke about the polynomial method and the proof of the Erdos-Turan Conjecture. And in the slides for that talk, I actually had fairly complete proof, which is one of the few times in these talks I'll have a complete proof. For one thing, I know when I'm sitting in an audience, it's hard for me to follow a proof with details. But these slides will be available somewhere, and several people have already emailed me and asked for copies of the slides, and I sent them out already. So yesterday's method was algebraic, and today's method is combinatorial. So let me just review a little bit what I did at the end of the talk yesterday. As usual, we take a set of non-negative integers, and the h-fold sum of the set A just consists of all numbers you can write as the sum of h elements of A, not necessarily distinct. And we say that A is an asymptotic basis of order h if this h-fold sum set contains all sufficiently large numbers. That is, you might miss a finite number, but all sufficiently large numbers have to be in the sum set. So for example, if you take the squares are not a basis of order 1, 2, or 3, but they are a basis of order 4. If you take the cubes are an asymptotic basis of order 9. They're also an asymptotic basis of order 8. You miss a few numbers. They're an asymptotic basis of order 7. You still miss a few numbers, but only finitely many. And one of the oldest open problems in additive number theory is to know exactly what is the nature of the cubes as an asymptotic basis. That is, what is the order of the cubes, the exact order. And this is a problem that's been around for a long time. So if you have a sum set, for any number n, you can look at how you can represent it as the sum of h elements of the set. And the representation function, R of n, A is the set, h is the number of sum n's, is simply the number of ways you can write n as the sum of h elements, the number of h tuples that add up to n. So to say that you have an asymptotic basis of order h means the representation function of n is at least 1 from some point on. And the famous conjecture of Erdos-Turan says that if you have a set of non-negative integers that's an asymptotic basis of order h, you cannot have a bounded representation function. So for whatever reason that no one knows, it seems that you simply cannot construct an asymptotic basis even of order 2 where every number has at most 10 to the 10 to the 80th representations. I mean, that may be the number of particles in the universe, but it's not necessarily a bound for the number of representations. And this is unsolved. The problem was originally stated for bases of order 2. It's natural to ask for bases of any order, but it's certainly unsolved for the original case of h equal to 2. Recall that if you have a set A, the counting function just counts the number of positive elements in the set up to n. So for various reasons, we don't count 0. And it's a very easy fact that if you have an asymptotic basis of order h, the growth of the set A, the number of elements up to n, has to grow at least like n to the power 1 over h. And it's simply a counting argument. Everything in this talk today is a counting argument. Since 0 is not counted in A of n, there are most A of n plus 1 elements of the set up to n. The number of h tuples is at most A of n plus 1 to the h. And if you can write every number greater than or equal to n naught as an h tuple, as a sum of h elements, you get this inequality and you take the h roots and you get the theorem. And we say that a basis is thin if in fact this minimum rate of growth is the rate of growth. So there are constants, there's some constant c, so A of n is less than c, n to the 1 over h. So a basis of order h with that property is called thin. And one of the first results, that goes back a long time, to Rakoff and Stur, say that there actually exists, you can construct thin asymptotic bases of order h. And there's a beautiful theorem of Cassel's, which for some reason he published in German. And it's the only paper that I know of that he didn't write in English, where he proves, in fact, for every h, you can construct an asymptotic basis of order h, which is not only thin, but the kth element of A is asymptotic to ck to the h with this error term. Okay. Now, thinness is one notion of a sparse basis, a basis that doesn't have too many elements. A different notion of sparseness in some sense is what we call a minimal basis. And we say that an asymptotic basis is minimal if no proper subset of the set is still an asymptotic basis. Now, since you're allowed to miss a finite number of integers in the sum set, to say that you have a minimal asymptotic basis means that for every element A in the set, or A naught in the set, there are infinitely many numbers that cannot be represented without A naught. So it really is a very strong condition. And to construct these, or even to prove they exist, is not a completely trivial matter. If you want to say, well, what this set E sub A, this is just the set of elements in the sum set that you lose that are no longer represented if you delete the element of A, element A. So if you take the h-fold sum set and you look at the h-fold sum set of A with this element little a deleted, the difference set is just the elements that you lose. And to say you have a minimal asymptotic basis means that this set E sub A is always infinite. It's infinite for every A in the set. And you can have a somewhat stronger notion of minimality if this set of missing elements, elements that are destroyed by the removal of the element A, is as large as possible, which is order A of x to the h minus 1. That's not a critical thing, but it's... So, as I said yesterday, sitting around as a graduate student, I thought if I couldn't prove the Erdos-Turan Conjecture, I would just construct a counterexample to it. And the idea was that if the conjecture were false, then a counterexample might be might be an asymptotic basis that was simultaneously thin and minimal. And do they exist? So yes, they do exist. For every h greater than or equal to 2, there are strongly minimal asymptotic bases of order h and even thin ones. And the first example was this simple. Let x be the set of all finite sums of distinct even powers of 2, y the sum of the set of all finite sums of distinct odd powers of 2. The union of those two sets is simultaneously thin and a minimal asymptotic basis. So, But unfortunately, this set and every other constructed example of a thin minimal asymptotic basis fails to have a bounded representation function. I mean, if you look at the representation function, it tends to be pretty small, pretty small, pretty small, and then it peaks, jumps, and then small, 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 and then damn it, up again. So no one knows why. I certainly don't know why. And as I said again yesterday, there is no classification or structure theory for thin bases or for minimal asymptotic bases. We can construct various examples. Lots of people have constructed different types of examples, but they're all like, isolated flowers that you find in the forest. You still don't know any connection between them or any way to classify them. But if you're talking about a minimal basis, it's natural to ask, if you have a basis, does it always contain a minimal basis? And there's one sort of trivial example for which that's not possible. If you just take the number 1 together with the even integers. So this is a basis of order 2, because every odd number is 1 plus an even number, and every even number is a sum of 2 even numbers. At least every even number starting, well, even 2 actually is 1 plus 1 here. So this is a basis, but it doesn't contain a minimal basis. And why is that? Well, if you delete the number 1, you just have even numbers, so you can't get any odd numbers. It's not a basis at all, so you couldn't get rid of the number 1. If you delete like the number 6, you'll no longer get the number 7 in the sum set. If you delete the number 50, you won't be able to get 51 in the sum set. You can delete any finite set of even integers. You'll lose that same number of odd numbers in the sum set, but you can't delete an infinite set. And there's a principle that we'll use several times today, which is that in an infinite set, there's no maximal finite set. So from this, you can delete any finite set of even numbers, but no infinite set. So there's no maximal set you can delete to get a minimal basis. A more interesting example is the following. If you look at all finite sums of distinct powers of 3 and together with numbers that are of the form 2 times the power of 3, this is also an example of an asymptotic basis, no subset of which is minimal. Right? Yeah. But the nicest example was constructed with Erdos a long time ago. It's slightly better than the previous example. It says that there exists an asymptotic basis of order 2 such that for every subset of A, every subset F of A, if you delete F from A, it is still an asymptotic basis if and only if the set is finite. So here, any finite set can be deleted. No infinite set can be deleted. And again, because there is no maximal finite subset of an infinite set, this set A, which is constructed, doesn't contain a minimal asymptotic basis. And I want to just sort of run through a bunch of slides that will be incomprehensible, but will be available wherever the slides turn out to be available, because it involves a lemma that is very useful. So this is the lemma. Now, a picture makes it very simple, but it is above my pay grade to figure out how to draw a picture in Beamer. So, yeah. So this is the lemma. Take a set of odd integers. Where are they? 2qk plus 1. And they grow exponentially fast. So qk is at least 5 times the preceding number, qk minus 1 plus 3. And then I look at this set. So these square brackets means the interval of integers. Every integer from here to here, together with every integer from here to here. And the idea is, in a set, if you're going to write the number 2q sub k plus 1 as the sum of 2 elements, one will be at most q sub k, and the other will be at least q sub k plus 1, right? There's like a smaller one and a larger one. They're symmetric around the half. Now, I'm trying to construct a set where the sum set contains none of these numbers, but almost everything else. So I'm going to take numbers. See, I don't want to be able to get a number of the form 2q sub k plus 1. So this interval starts at 2q sub k minus 1 plus 2 up to this, which is less than qk. This is a little bit bigger than qk. It's a small interval. This is a very big interval. This is a small interval, qk plus 1 up to qk plus q sub k minus 1. And if you were to draw a picture of this, you would see that if you look at pairs of numbers symmetric around q sub k and a half, let's say, you might have a number here, but the corresponding number wouldn't be here. So no two of these numbers will add up to this guy. And if you take this set of numbers, it's just a little calculation. It's nice. I mean, I'll show it in a second, but it's sort of. So if you take this sum set, it's contained in the complement of Q. So if you take 2 elements of this set and add them together, you'll never get one of these. But what you will get is almost all other numbers. So this squiggle, you write one set is like this squiggle with another set, means they coincide from some point on. So this statement means that if I take the sum set, this set added to itself, you get all numbers with finitely many exceptions in the complement of Q. But there's actually a kind of stability to this. If you perturb the set A sub Q slightly, either you delete a finite number of numbers or you add a finite number of numbers, it doesn't make any difference. Right? You're still going to get essentially all numbers outside of Q. Well, I apologize. This is actually a proof of that statement. You know, if this were a lecture in a classroom with chalk and you know, a bunch of graduate students, it would take me a half an hour to go through this. But I mean, you can sort of like extract it from this, but not sitting at a desk, I believe. But there is a proof, and this is basically it on the slide. And from that, one can prove this theorem. I want to point out, this has to do with bases of order 2. And there is a common phenomenon in this subject where you can prove something about bases of order 2, but not necessarily for bases of order 3 or higher. So it's not known, if you take an h at least 3, whether or not there exists an asymptotic basis of order h with this very pretty property that any finite subset can be deleted and it still is an asymptotic basis, but no infinite set. And so this is the idea of the proof using the lemma. We constructed this set A sub q, which was a union of these two intervals. And so that is, I had a set, this was a union of sets. Each of these sets was like an interval less than q, and an interval bigger than q. This is a huge interval, this is a tiny interval. And I want to construct a set A sub k, a finite set, which contains these two unions of intervals and a few more elements. And there's a sneaky way to do it. It's like, so you have to have this sort of picture. You have this odd number, 2q plus 1. You want to be able to write it as a sum of two things. One's going to be less than q, the other's going to be bigger than q. So if you take a number that's in the set, and if you take a number that's in the set, call it A sub k minus 1, if you add 2q sub k plus 1 minus that, then in this new set, you'll be able to represent 2q sub k plus 1 as a sum of 2, because this guy is already in this set, and you've added a sort of complement with respect to this. And you do it in such a way that each of these numbers that you're adding, for each of these elements of the set, you pick it exactly once. And if you think about this for a little bit, you'll see that you'll get every single number. So that set A that you're constructing, the union of these A sub k's, is an asymptotic basis of order 2. And you can dilute any finite number of them. It doesn't matter. But for every number you delete, you're going to lose a 2qk plus 1. So if you delete a finite number of elements, you'll lose finitely many of these. You still have an asymptotic basis. If you delete infinitely many, you lose infinitely many numbers, and you no longer have a finite basis, a basis of order 2. So that is sort of the idea of the construction. It's curious. What about thin bases? I said they exist, but I haven't described how to construct them. So let me just give, there's a whole large literature on this now. But let me just give one very simple construction in a very special case. So if you take a set of non-negative integers by f star of w, I just mean all the non-empty finite subsets of w. And so associated to the set w, I can look at all numbers which are sums of powers of 2 over all these non-empty finite sets. Since the sets are non-empty, you don't have 0 in here. These are all positive integers. So for any set of integers w, a of w is the set of all numbers which in binary can be written as sums of a finite sum of powers of 2 where the powers all belong to W. And there are a couple of nice properties of these. They're just a sort of a series of simple lemmas, but they became sort of standard in this subject and are referred to a lot. If you take two disjoint sets of non-negative numbers, there are these binary sums are disjoint. If your set W of X is very regularly spaced, it's not just that it has density theta, but the number of elements in the set W up to X is theta X plus some constant big O of 1, then the set A of Wx has growth function like X to the theta, above and below. And then the key part is that if you write the non-negative integers as a union of H sets, and you look at the corresponding sets of numbers with these appropriate binary expansions, this is an asymptotic basis of order H. I mean, that's just the binary expansion of numbers. That's not too exciting. But then there are a couple of curious facts about these binary expansions. So, I mean, here's a number. You write it in binary. It's the sum of distinct powers of 2. So these are distinct exponents. So suppose you take this number and you write it in a different way as a sum of powers of 2. Well, you say you can't write it in a different way. There's only one way to write a number as a sum of powers of 2. But of course, that's not true. You can write 4 as 2 squared, and you can write 4 as 2 plus 2. So on the left-hand side, these exponents are distinct. Here, they're not necessarily distinct. But it's just a curious little fact that whenever that happens, you can actually partition this set so that each of these powers of 2 is a sum of a subset of these numbers over here. Right? It's some kind of like property in chemistry where you're putting atoms together somehow. Excuse me? No. Well, I mean, suppose you had, 8. I mean, the only part of that's unique is the sum of distinct powers of 2. But the curious fact is, if you write a number as a sum of not necessarily distinct powers of 2, you can just collect them into little bits, rearrange them. So each is a power of 2, and they're distinct powers of 2. So you recover the usual binary expansion. Let's skip this. Let's skip this. So the upshot of all this, right? I mean, details are available for whoever likes to see them. But if you take the simplest case where you partition the integers into congruence classes mod H, and you look at these at this set A, so this is the set of all numbers that are sums of powers of 2 where the powers are all 0 mod H. And here are sums of powers of 2 that are all 1 mod H and so forth. This is thin and strongly minimal. And this has been extended to geodetic things. I mean, there's some technical complications along the way, but yeah. But this gives you very, very sparse minimal bases. Now, what about fat minimal bases? How large can a minimal basis be? So the ones we've seen so far have all had density 0. So there's a construction with Erdos that says the following. So for any h greater than or equal to 2, you can these are all constructions in some sense. There's a minimal asymptotic basis of order h with density 1 over h. So there's a minimal asymptotic basis of order 2 with density 1/2. And in fact, for every alpha from between 0 and 1 over 2h minus 2, there's a minimal asymptotic basis of order A and with this density alpha. So in particular, if h equals 2, this is just 0 to 1/2. So this says that there's a minimal basis of there's a minimal asymptotic basis of order 2 with density alpha for every alpha between 0 and 1/2. And this gap between 1 over 2h minus 2 and 1 over h has been filled in over the years. There's actually a very beautiful result by Janczak and Schoen for order 2, where you can construct a minimal asymptotic basis of order 2, where the counting function is almost exactly n over 2. A of n is it's like between n over 2 and n over 2 plus 1. That's not a big interval. But they couldn't deal with the case of bases of order h greater than or equal to 3. So it is still an open question whether you can have a whether you could have a minimal asymptotic basis of order h, whether you have a minimal asymptotic basis of order h with a of n equal to n over h plus big O of 1. All right, that's right. Now, I said that for bases of order 2, we constructed minimal asymptotic bases of density alpha for every alpha between 0 and a half. Was that the limit of our method or the state of nature? Could there be a minimal asymptotic basis of order 2 with density greater than 1/2? Or more generally, a minimal asymptotic basis of order h with asymptotic density strictly greater than 1 over h? So the answer should be no. And sometimes it happens that what should be is what actually is the case. The answer is no. But I'm going to show you a proof of that fact, which uses excessively powerful machinery. And there should be like a trivial one-line proof of this, but I don't know it. And the proof is going to use Knaser's theorem on the asymptotic density of sumsets. So let us recall that, remember, a of x is the counting function of the set x. A of x over x is between 0 and 1. You take the lim inf, and that's the lower asymptotic density. And again, if the limit exists, then it's simply called the asymptotic density, and we don't write the L. Again, we write A, the squiggle B means that A and B coincide from some point on. So n, an integer n is in the set A, if and only if n is in the set B for all n, greater than or equal to some n naught. And also, if you take a positive integer g, you can take the set A and just extend it by adding the complete congruence class modulo g to every element in the set A. So A superscript g, it's all integers n, where n is congruent to A mod g for some A in the set A. And the special case of Knaser's theorem that we use is the one I mentioned yesterday. If you take any set B of integers, so if things were just, or just right, or what you might expect naively, you would expect that if you add the set B to itself h times, the density is at least h times the density of B. But we saw examples yesterday where that doesn't happen. The most trivial example, again, is just take the even numbers. The even numbers have density a half, and 2 times a half is 1. But if you add the even numbers to themselves, you just get the even numbers. So on the left-hand side, you have a half. And because a half is not greater than or equal to 1, this isn't true. But Knaser tells us that if this isn't true, that happens only in a very, very special case. And that is where B has a very special kind of structure. B is essentially a union of congruence classes. And this basically reduces to the Cauchy-Davenport theorem. And the Cauchy-Davenport theorem, there's that -1 that you see. And that's the -1. So Knaser's theorem says that if this inequality fails to hold, then there's a positive integer g such that when you expand B by filling it out with the complete congruence class mod g, the h-fold sumset of B and the h-fold sumset of these congruence classes, they coincide from some point on. You're only missing finitely many numbers. And the density of it, now of course, this is a union of congruence classes. So if there are congruence classes, this has an asymptotic density R over G. The limit exists. So, and if these two sets eventually coincide, the density of this is the density of this. I can drop the L here for the D. So the density of the H-fold sum set is greater than or equal to H times the density of B minus H minus 1 over G. Right? By the way, there's one important thing to note here. Suppose you have a set B whose density is bigger than 1 over H. So if B has density bigger than 1 over H, H times that is bigger than 1. Right? But this is a set. The density of any set is at most 1. So if B has density bigger than H, this inequality fails, and it has to be this case. Right? So Sarkozy and I proved the following. If A is an asymptotic basis, well, this will lead us to where we want to go. If A is an asymptotic basis of order H, and if A contains a subset whose density, lower asymptotic density, is strictly bigger than 1 over H, which means A, of course, is density strictly bigger than 1 over H, because this is a subset. Then there's a finite subset F that is elements of A, which are not in B, where if you take that finite subset B and add it F and add it to B, this becomes an asymptotic basis of order H. Right? Okay, so we're going to use Combinatorics theorem. Of course, if B is an asymptotic basis of order H, you're done. Just add the empty set. So suppose B is not an asymptotic basis of order H, which means HB does not eventually coincide with the set of all of the non-negative integers. And because the density of B is greater than 1 over H, the density of HB, which is less than or equal to 1, is strictly less than this. So we're in the second case of Combinatorics theorem. And that means there's some modulus G such that when you complete the set B, just make it the union of all the congruence classes with representatives in B, the H-fold sum set of B coincides with this set of congruence classes, mod G. And we have this inequality then, that H times, times the density of B minus H minus 1 over G is less than or equal to the density of the sum set. And of course, the density of the sum set is the density of a union of congruence classes. If there are congruence classes, the density is R over G. And it can't be equal to 1 because B is missing infinitely many numbers. So this set is missing infinitely many numbers. So it can't be all congruence classes. It's missing at least one congruence class. So the density is at most 1 minus 1 over G. Now, the density of B is greater than 1 over H. Let's say it's 1 over H plus delta, and so H times the density is 1 plus H delta. If I take this and plug this into this inequality, I get this. Right? And rearranging, it actually gives us a bound for how large the modulus G can be. So G is some positive integer which does not exceed H minus 2 over H delta. Of course, if we're dealing with bases of order 2, we're done, because there is no such G, so we're just done. So this is really only serious when H is 3 or greater. So, where are we? B was a subset of A. B is a subset of this union of congruence classes. It could be that the set A, which contains B, is also contained in this union of congruence classes. But if that were the case, we know that A is a basis of order H, so N and HA eventually coincide. But if A is contained in this set, then HA is contained in this H-fold sum set, so these coincide, which coincides with the H-fold sum set of B. But we started off with the fact that B was not an asymptotic basis of order H. This is impossible. That's a contradiction. So A cannot be contained in this union of congruence classes, which means that there's some element, let's call it C1 in A, which is not congruent modulo G to any element in B. So let's just call this modulus G, G1. And let's take a new set B1, which is just the original set B, with this one element C1 added. Now, of course, if B1 were an asymptotic basis of order H, we'd be done. It would be B union one element. But if it's not an asymptotic basis of order H, the density is still the same. We just added one element. So there has to be G2 satisfying these same bounds, and an element C2 in A, which is not congruent to B mod G for any B or for all B in the set B1. Right? And we repeat the argument. So what happens? As we go along, we're computing a sequence of positive integers moduli. We're all in this bound, so there are only finitely many possible moduli. And at each step, we're choosing an integer C, which isn't congruent to B mod G. For any element, like Ci is not congruent to B mod G, for any B in the set B sub I minus 1, which is this. But this process has to terminate because there are only finitely many moduli, right? There are only finitely many G's that satisfy this inequality. And so there are only finitely many different congruence classes modulo a modulus bounded by H minus 2 over H delta. Therefore, there is a finite set of elements in A where B together with that finite set is an asymptotic basis of order H. All right? So we actually got to use Canesius theorem. So that says, for example, that if you take a number tau between 0 and delta, A is an asymptotic basis of order H of density 1 over H plus delta. There's a set W in A whose density is tau. And you can remove that set of positive density and you still have an asymptotic basis of order H. And the proof is basically one line. If you take any subset of A of density tau, and if the set has lower density 1 over H plus delta, you can find a set with asymptotic density tau, and that B be the complement. So the density, the lower density of B this is a subset of this, so the lower density is just the difference. This is positive, so it's strictly bigger than 1 over H. So there's a finite subset F of the difference, the complement of B and A, where B union F is an asymptotic basis, and we let W be this set. So what this says is if you have an asymptotic basis of order H of density greater than 1 over H, there's actually a set of positive density you can remove, and what's left is still an asymptotic basis. Which means if you have a minimal asymptotic basis, the density is at most 1 over H. Because if it were bigger, strictly bigger than 1 over H, you could throw away a huge amount. And what is, in some sense, a problem, maybe it's a meta problem, is prove this result without using Canesius theorem. That's, I don't know why we need to have such an argument that we used. Oh, wow, okay. Someday I will learn how to deduce from my slides the length of my talk. So in additive number theory, there's a general problem. To extend results about bases of order 2 to bases of order strictly greater than 2. One of the reasons for this is the following. If you have N is a sum of 2 elements and they're different representations, then the A1 and the A2 are disjoint from the B1 and the B2. For example, 5 is 1 plus 4 and it's 2 plus 3. And 1 and 4 is disjoint from 2, 3. But if you have representations with more than three or more sum-ends, then it's possible for the sum-ends to intersect. For example, 1 plus 2 plus 4 is 7, and 2 plus 2 plus 3 is 7. But you have the same number in both of them. And this has always been a problem in these types of additive questions. very often for combinatorial reasons, especially when you're trying to use probabilistic methods and you lose some independence. So this is this phenomenon has been relabeled. It's now, there's a whole subject about additive energy. And, but it basically comes down to the fact that you can have multiple representations with the same summands. Okay, that's really all I wanted to say today. I just wanted to make a couple of bibliographical remarks. So there is a great paper by Alfred Sturr that was published in Krella 65 years ago, I guess. Wow. This was a survey, solved and unsolved problems in about bases for the natural numbers. And this, at the time, it was like the major survey of this field. And when I was a graduate student, I didn't know the paper existed and I hadn't read it. So I came up with this idea of minimal bases because I wanted to deal with the Erdos-Turan Conjecture. And I sent off my little paper to a journal, and they sent it back and said, but you didn't discover this concept. It's actually was defined by Sturr. So, of course, I looked up his paper and learned some German. And Sturr actually he liked the idea of a minimal basis, but he wasn't sure what the definition of a minimal basis should be. So he gave 7 or 8 different definitions of minimal bases. One of which was exactly mine, though in his paper he didn't know whether any of these things existed. But the definition is clearly there. But he had a PhD student named Erich Herter. And so the year later, Herter has this paper, a contribution to the theory of minimal bases, where he proves the existence of minimal bases of the type that I was interested in. In fact, he proves there are uncountably many of them, but he didn't have any example. So whereas I didn't have uncountably many, but I had a concrete example you could hold in your hand. And since then, there's been a lot of, there's just a few random papers that are here that are interesting, but they're more. Tomorrow, I'm going to talk about, so my paper was rejected, right? Because they said, you didn't invent this and we already know they exist. And at the time, I was teaching in Illinois and my family was in Philadelphia. And I would get in my car early in the morning when it was like a vacation time, and I would drive for 14 hours or so, or more, straight home. And so it's it's a situation conducive to having your mind wander. And as I was driving home, I thought about the even numbers. Well, of course, the even numbers are not a basis, because if you add the even numbers, you only get the even numbers. But they have this property, so you might call it a non-basis. A non-basis is a set that is not a basis. But the even numbers have this property that if you take any number that's not in the set and you add it, it becomes a basis, because any number that's not in the set is an odd number. And once you have an odd number plus all the evens, every number is a sum of 2. So you might call the even numbers an example of a maximal asymptotic non-basis. And of course, that's like a trivial example, and you can construct other examples by choosing sets of congruence classes in the right way. And with a little bit more work, you can find rather non-trivial examples of maximal asymptotic non-bases that were not unions of congruence classes. So I took my old paper, I added this, and I sent it to the Journal of Number Theory, and they published it. Of course, there was something that they thought was new. I actually liked the original example. And tomorrow's lecture is a preview of coming attractions, is about maximal asymptotic non-bases. That's what I'm going to talk about. And then we will get to, I should say this also. Erdos was a great guy. I didn't know him at all. I was like a graduate student somewhere. And I wrote this paper, and at the end of my paper, I had some unsolved problems. And I sent it to Paul Erdos, Hungarian Academy of Sciences, Budapest. He got the paper, looked at the unsolved problems, sent me a solution to one of them. I looked at his solution, and it didn't make any sense to me. I didn't understand it. So I worked at it really hard. And let's say if the problem were to prove A, if you actually sort of figured out what he was doing and twisted it a little bit, he gave a proof that A wasn't true, but that the opposite of what he wanted to do was actually the case. And that was our first joint paper. And one of the problems that was in this early paper was the following. It was sort of a strange question, but it turns out to be pretty cool. You have the integers. So imagine you have a subset, which is a minimal asymptotic basis. That means if you take away an element, it no longer is an asymptotic basis. So suppose you actually do the following. You have the integers, and you partition into two sets A and B, where A is an asymptotic basis, and B is not. So A is a basis and B is a non-basis. But if you take any element of A and delete it and move it to the set B, your A with this one element gone is no longer a basis. And the set B with this one element added becomes a basis, which means that you actually have a partition of the integers into two sets, one of which is a minimal asymptotic basis, and the other is a maximal asymptotic non-basis. So this property flips. As you go from here to here, it changes. So it's not obvious whether such a thing could happen. But if it were to happen, you might say, well, okay, that's cool, but suppose you do it again. So you have this partition of the integers. You have A and B, basis, non-basis. You take a guy here, move it over here. Now it's non-basis, basis. Then you take a guy here, any guy, put it over here. Flips again. Now this is back to being a basis. This is back to being a non-basis. How often can you do that? If you just start at random, taking elements from one side and put it to the other, an element from here, it would oscillate forever. So if I'm lucky, tomorrow I will show you a proof that such a thing exists. It's a paper by Erdos and I that I don't think anyone's ever read, but and there was always this sort of this complication in our joint work, where Erdos liked to give probabilistic arguments for things. I just don't like probability. At least I have no emotional connection to it. So if there's a probability argument that I can convert to a combinatorial argument, I do. So our paper, since I write up the papers, our paper was purely combinatorial. But you can tell that there's a probabilistic basis to the argument, because it really just comes down to like a pigeonhole principle thing. You try to do something, and there has to be something left. It's like, all right. Anyway, that's what I'll do tomorrow. Thank you.